Good day to everyone out there in YouTube land. This is Professor Friday from Macomb Community College coming at you one more time. I have just enjoyed a delicious breakfast of Jimmy John's. It's always good to start your day out with something healthy. Well, healthy. So, we've had a request from a Calculus 2 student to do a problem that is like problem number 7 from the WebAssign homework. This is the integral of 15 over secant of x tangent of x dx. Now, normally what we're used to seeing is not trig functions in the denominator. So the first thing that I'm going to do with this integral is use a couple of fundamental identities. Secant of x, we'll use the reciprocal identity to call that 1 over the cosine of x. And tan of x, we'll call that sine of x over cosine of x. Now, this does not make our integral a whole lot nicer because now we have fractions inside of our fractions, so recognizing that the cosine of x is in the denominator of each of those, and also going to factor that 15 out. We can call this cosine squared of x times sine of x to the minus 1 power. Now, quick note about this, this is not an inverse sine. This is a multiplicative inverse, but not a functional inverse. So, the way that we're going to approach this problem today is as though we have an odd power of the sine of x. Now, let's make a note of this. Odd power of sine x. The technique in class that we discussed was we are going to set one of those signs aside so that it can become a du. Allowing us to use a u substitution of u equals cosine of x. However, there is a bit of an issue because, well, we only have -1 sides. How are we going to take one away from that? The answer is forcibly. So here's what we'll do. We'll keep our cosine squared x in place, and we'll borrow 1 from the -1 power. We'll call that sine of x to the -2 power and set aside our sine of x dx. This is a little trick that we refer to as multiplying by 1. We're essentially multiplying by sine of x and dividing by sine of x in the same step. Now what this does for us is we can now rewrite the expression as cosine squared x over sine squared x times sine x dx. We're just about ready for our substitution. However, our substitution is u equals cosine of x. We need this entire expression in terms of cosine of x. So what we're going to do is apply a Pythagorean identity, like so. Then our integral will become, let's see, we got cosine squared x over, this will be 1 minus cosine squared x times sine of x dx. That looks ready for a u substitution. Now, given that du is negative sine of x dx, our sine of x dx will become negative du. I think that's enough for us to go on. So this will be 15 times cosine squared x will become u squared over 1 minus u squared times negative du. So from here, the question becomes, where do we go? First thing I'm going to do is distribute the minus sign through the denominator. This is one possible interpretation of what to do. We'll get u squared over u squared minus 1. And we still have du. So from here, the question is, where do we go? Now, ordinarily, I'd say, well, it's a rational function, so let's do a partial fraction decomposition. But we haven't exactly hit that section yet, so the question is, where do we go? We are going to use a very tricky move here that is referred to as adding 0. My denominator is u squared minus 1. So I'm going to try to introduce a factor of u squared minus 1 in the numerator. I can do so by subtracting 1 and then adding 1. And then we can give them their own individual fractions. We'll do u squared minus 1 over u squared minus 1 plus 1 over u squared minus 1 du. Now from here, I'm going to head back up here. Like so. I'm going to reduce that fraction down, and we'll refer to that fraction as 1 plus 1 over u squared minus 1. Now once again, now that we've talked about section 8.5 in the textbook, this is a rational function and we can perform a partial fraction decomposition, or if we are really slick, we will recognize that from section 5.8. This is the derivative of an inverse hyperbolic function. Question is, which one? I'm fairly confident we came up with 2 of them. I'm going to reference my book though, because I like to be absolutely sure about these things. Let's see. Section 5.8, section 5.8. There we go. We have some inverse hyperbolic functions in here. If I'm not mistaken, what we have looks a little bit like the derivative of the inverse hyperbolic cotangent. Come on, focus. Or the inverse hyperbolic tangent. Problem is, those look like 1 minus u squared, and what we have is u squared minus 1. We can account for that using a negative sign. So we'll call this the negative inverse hyperbolic tangent of u. Now because our integral is done, we can tag on our plus c at the end. However, the original expression was in terms of x, so shall ours be. So u, we said earlier, is equal to cosine of x minus the inverse hyperbolic tangent of the cosine of x plus c. That is good enough for a final answer. Now, as always, answers can vary slightly based on techniques of integration used. In addition, if you had used a partial fraction decomposition at any point in here, we probably wouldn't have an expression like this, but we would have one that involves a natural log of a couple things. So this is what I came up with. I hope you enjoyed, and have a great day.